the lucky guess for this harmonic oscillator with sinusoidal forcing? Yeah. You would guess that y particular looks like a cosine t plus b sine t. Yeah, it's the same thing. That's fine. A sine plus b cosine is the same thing. All right, is the forced response the same as the forcing function? No. The forcing function is the thing in the original differential equation. The forced response is the solution, is your particular solution. So these things are not the same. And which sinusoidal forcing function is associated with the real part of a complex particular solution? No. Oh, yeah, it is cosine. It's cosine. Yeah. So what the force? No, because I'm just talking about the forcing function, which is only sinusoidal today. Sure. Yeah. So remember that e to the I theta is cosine theta plus I sine theta, right? So if you find a complex solution that looks like e to the I theta, the real part of that is associated with a cosine forcing function. The imaginary part is associated with a sine forcing function. All right, so I just want to pull up the calendar for a second. Remind you, your quiz 5 is due today, so put that in the folder. A couple people still have a few things to finish. It's okay if you give it to me later today, no later than like say 2 o'clock or so. You have another take-home quiz coming up next week. Yeah, next week. And then you've got test 3 coming up. So I will get you a review for test 3 at least a week in advance. Okay. All right, so sinusoidal forcing happens frequently when you're using a differential equation to model a system. It could model the shaking of a building in an earthquake, or sound waves pushing against glass. So if we use the methods from last class, we can solve this sinusoidal forcing differential equation. All right, so last class there were 3 steps, right? First you have to solve the associated homogeneous. So we have to solve y double prime plus 2y prime plus 2y equals 0. All right, so somebody remind me, how do I start this? Yeah, so you start by writing down the characteristic equation, s squared plus 2s plus 2 equals 0. You can get it right from the original differential equation. And when you solve for this, what are you getting? What are those s's? They're eigenvalues, yeah. So does this factor? No, so I got to use the quadratic formula. So we're going to have s is -2 plus or minus the square root of 2 squared minus 4 times a times c all over 2a. So s comes out to -2 plus or minus the square root of -4 over 2, which is -1 plus or minus I. Everybody okay with that jump in arithmetic? Okay. So I've got eigenvalues, -1 plus or minus I. Those are important. Now, when you get a complex eigenvalue, that means we've either got a spiral sink or a spiral source. Which one do I have in this case? A sink, a spiral sink, because the real part is negative. So we've got a spiral sink. And the way I get the solution, right, is I can just pick one of the eigenvalues. So my y sub h for homogeneous, solution to the homogeneous equation, is going to be take one of my eigenvalues, and it's e to the lambda t I'll do -1 plus I t. I don't need the vector v that goes with the eigenvalue -1 plus I, because I only care about finding the solution y. I don't care about finding y and v. Okay, so I don't need the eigenvector. So then I simplify this. Well, I distribute the t, and I get e to the -t plus it. And then I can use a rule of exponents that rewrites this as e to the -t times e to the it. Because when you have like bases, you would add those exponents, so I can rewrite it that way. And then replace e to the it with cosine t plus I sine t. Euler's formula. Right. Yeah, so it turns out that this is a complex solution. I shouldn't have put the h's there yet, sorry. Because it's not the final thing. We're not done yet. So that's a complex solution to the homogeneous equation. And then to get the general solution to the homogeneous equation, you take the real part with a constant and add the imaginary part with a constant, and you drop the i's. So I'm going to have k1 e to the -t cosine t, that's my real part, plus k2 times the imaginary part, e to the -t sine t. Just a linear combination of the real part and the imaginary part. Okay, so there's my solution to the homogeneous equation. All right, nothing new yet. Step 2, we have to find a particular solution to the forced equation. So y double prime plus 2y prime plus 2y equals sine of t. Okay, so in the quiz, I asked you what would a lucky guess be if you have a sine of t as your forcing function. Whether you have sine of t or cosine of t, any sinusoidal forcing function, your lucky guess for y particular would be a cosine t plus b sine t. Okay. So, and that works because you need to be adding the second derivative, the first derivative, and the function itself, and you need to get sine t. So a plain sine or a plain cosine won't work because you're always going to be introducing the other one when you take derivatives. So you need a combination of both of them to get this to come out to sine t. All right, so then we take y prime. The derivative of a cosine t would be -a sine t. And the derivative of b sine t would be b cosine t. And then y double prime is -a cosine t minus b sine t. Then we plug in y prime, and y double prime into the equation, solve for the a and b to make it equal sine t. All right, so y double prime, -a cosine t minus b sine t. There's my y double prime. Plus 2 times y prime, which is -a sine t plus b cosine t, plus 2 times y, which is a cosine t plus b sine t. And that has to all equal sine of t. So I just have to figure out what a and b will make this true. Yeah. Yeah, I think what I'm going to do is I'm going to gather all my cosines and gather all my sines, and then equate coefficients with the other side. Because how many cosines do I have on the right? None. So whatever my coefficient on cosine is on the left would have to be 0. And whatever my coefficient on sine is on the left would have to be 1, because there's a 1 there. So I'm going to distribute my 2's, and then I'm going to gather all my cosines, gather all my sines. All right, so I've got negative a cosine t minus b sine t minus 2a sine t plus 2b cosine t plus 2a cosine t plus 2b sine t. And I need that to all equal 0 cosine t plus 1 sine t. Does that make sense? I just added a 0 cosine t to the right. Okay, so now I'm going to gather all my cosine terms. So I've got this one, and this one, and this one. So altogether, when I add them, I have negative a plus 2b plus 2a. So that's going to be a plus 2b, a plus 2b cosine t's. Right, and then I'll do my sine t's, gather all those up. Negative b minus 2a and plus 2b. So that would be b minus 2a. And that's got to equal 0 times cosine t plus 1 times sine t. And then we just equate coefficients. The coefficient on cosine on the left is a plus 2b, and on the right it's 0. So those things have to be the same. So a plus 2b has to be 0. And my sine coefficient on the left is b minus 2a. And on the right, it's 1. So b minus 2a has to be 1. And then we just solve this system. So yeah, a is negative 2b. And then substitute in here, and I have b minus 2 times negative 2b equals 1, which means b plus 4b equals 1. So b is 1/5. And then we come back over here, and a is negative 2 times 1/5. A is negative 2/5. So that means I just found my y particular, right? My y particular was, what did I do first? Cosine? A cosine, yeah. So it's negative 2/5 cosine t plus 1/5 sine t. There's my y particular. So I'm not quite done. The last step is what? Add the yh and the yp. The solution to the homogeneous and to the particular solution. So I got to remember what they were. So my y general was my yh plus my yp. So I'll write that down. Solution to the homogeneous plus my particular solution, and that's k1 e to the negative t cosine t plus k2 e to the negative t sine t minus 2/5 cosine t plus 1/5 sine t. So there's the general solution. Using the same method that we used last class, the only new thing that we had to learn was what kind of guess do you use to find y particular. All right, but there is another method. People still writing? I'll take a second. All right, so now we're going to develop another technique for finding the general solution to an equation that has sinusoidal forcing. It will come in handy in later sections, so even though you don't need to know it right now because you can do what we just did, it'll come in handy. This is a good time to introduce this technique because it works for this. All right, so the general idea is we are going to complexify and solve the equation. So it's basically the same process as before, right? The three-step process. First, solve the associated homogeneous equation, right? We already did that, right? We got this. So that's done for us. And then instead of solving a sinusoidal forcing, solve it with exponential forcing. So replace sine of t with e to the I t. So we're going to do y double prime plus 2y prime plus 2y equals e to the I t. All right, so the question of why we're doing that will be answered in a few minutes, but we're going to look for a solution to this equation using lucky guess, particular solution. All right, so yeah, so you would guess alpha e to the I t, because that's what we typically guess when we have an exponential forcing function. So my y particular guess is going to be a e to the I t, which means that y particular prime would be I a e to the I t, just because of the chain rule. And then my y particular double prime is going to be I a e to the I t times I again, because of the chain rule, and I times I is -1. So this would be I squared a e to the I t, which is actually negative a e to the I t, because I squared is -1. All right, so then we plug into the equation and we find out what a value will make this work. All right, so y double prime is negative a e to the I t plus 2 times y prime, that's going to be 2I a e to the I t, plus 2y, so that's 2a e to the I t, has to equal 1 e to the I t. All right, I've got some like terms on the left-hand side here. Negative a e to the I t plus 2a e to the I t, that adds up to a e to the I t. So I've got a e to the I t plus 2I a e to the I t equals 1 e to the I t. All right, if I factor out e to the I t from the left-hand side, I'm left with a plus 2ai. And then equate the coefficients. So it's got to be that a plus 2ai equals 1. Right? The coefficient on e to the I t on both sides has to be the same for those equations, for that equation to be true. Factor out an a from the left, and I'm left with 1 plus 2y. And then to solve for a, just divide both sides by 1 plus 2y. And I did not give you enough room to write all this. Sorry. Because we're not even close to done. Okay, so that is the a value that solves the complexified equation. So a complex solution would be a e to the I t, where a is this complex number 1 over 1 plus 2i. That's just a particular solution to the complexified equation. So I was trying to solve y double prime plus 2y prime plus 2y equals e to the I t, and I found a y particular is 1 over 1 plus 2i e to the I t. All right, writing a complex number as 1 over 1 plus 2i is a little bit strange. We like to write complex numbers in the form a plus bi. So I'm just going to simplify that 1 over 1 plus 2i a little bit. So I'm going to do that by multiplying by the top and bottom of the fraction by the complex conjugate. 1 minus 2i over 1 minus 2i. So my numerator becomes 1 minus 2i. And then when I FOIL 1 plus 2i times 1 minus 2i, I get 1 minus 2i plus 2i cancel, plus 4i squared. Sorry, minus 4i squared. But what's I squared? -1, so my denominator is actually a 5 now. Which is 1/5 minus 2/5 I. Yeah, that's your A. It's just an equivalent. Yep. So now I'm just going to rewrite it as A, 1/5 minus 2/5 I times e to the it. You might recognize 1/5 and -2/5 from when we solved the problem before. Those were the values that we were looking for, the A and the B. They're going to show up in this also. Okay, so my y particular. I'm just going to write it one more time. 1/5 minus 2/5 I e to the it. Okay, so that's the y particular we found. Now I'm going to replace e to the it with cosine t plus I sine t. Obviously. 1/5 minus 2/5 I times cosine t plus I sine t. So this is good because we're looking for a solution to not the complexified equation that I wrote, but to a sinusoidal function. So now I have reintroduced sines and cosines, so this is a good thing. All right. So now I'm going to have to FOIL this. Right, I've got a binomial on both sides. So I'm going to have 1/5 cosine t plus 1/5 I sine t minus 2/5 I cosine t. And then I'm going to have minus 2/5 I squared sine t, but I squared is really -1, so it's plus 2/5 sine t. What? Yeah.
So it would be like A plus DI. Yeah, they do A plus BI. B was the something C. So in this case, we have B1.
I don't know. I don't know what you're referring to. Okay. All right. Next, I'm going to gather my real parts and my imaginary parts. Right. So that's real, and that's real. No I's. So I'm going to have my real part, 1/5 cosine t plus 2/5 sine t plus I times, and I'm going to gather my imaginary parts. 1/5 sine t minus 2/5 cosine t. Okay, this is a solution to the complex equation where the forcing function is e to the it. E to the it. What I'm really interested in is the solution where the forcing function is sine of t. But e to the it is cosine t plus I sine t. right? So I actually want the imaginary part, right? I actually only want the imaginary part of that complex solution. And that's the same particular solution we found when we did it with a lucky guess. 1/5 sine t minus 2/5 cosine t. So when I come back down here, it says since e to the it is cosine t plus I sine t, we're actually only looking for the imaginary part of the complex solution, right? Because I only want a forcing function of sine in this problem, right? That's because our forcing function is sine of t. If the forcing function were cosine of t, we'd have taken the real part of the complex solution. So my y particular is 1/5 cosine t minus 2/5 sine t. Did I get that wrong? Yeah. This should be sine, and this should be cosine. Yeah. I did not say it was easier. I said it was another way that will come in handy in the future, and this was just a convenient time to introduce it. You can do whatever you want on a quiz or a test. Yeah. It's negative over here. So the imaginary part, this is my y particular. So this negative 2/5, I don't know where you lost the sign, but it should be negative. Yeah. So again, we're not quite done. That's just the y particular. The very last thing is add the homogeneous solution to the particular solution, and you get the general solution. So just remember the general solution is y homogeneous plus y particular. So y general is, did I write it down? Nope. K1 e to the negative t cosine t plus, we've already written this down because we already solved this a different way, but it's important not to forget the big picture. Minus 2/5 cosine t plus 1/5 sine t. Okay. So now, and not any sooner than now, if you have initial values, you can use them to find values of K1 and K2. So you don't want to do it until you have the final general solution, until you've done the whole three-step process. Then you could try to find values for the constants. All right, so here are several solutions to the ODE that we've just been solving today. Solved two different ways. Graph several solutions of y versus time. Right? And you can see that they all tend towards one solution, right? The homogeneous solution always dies out because look at, they both have an e to the negative t term, right? So as t goes to infinity, those things are going to go to 0. Right, so the only thing left is the particular solution. So we call that particular solution the steady state solution, steady state sinusoidal solution. Okay, I'm going to let you try one. I did ask you to solve it using complexification because you've had practice doing lucky guess. So yeah, at least once use the complexification.